Alrighty, we're going to use the instantaneous rate of change, but we're going to evaluate or estimate that by the average rate of change. A of 15 minus A of 5 all over 15 minus 5, which gives us 25 minus 18 over 10, 7/10, or 0.7 gallons per hour. In part B, we are asked for the time interval from 0 to 30. Is there a time t at which A prime equals 1/5? Well, we know A of t is a twice differentiable function. And if that is the case, it is also continuous. And the mean value theorem applies. Since A of 30 minus A of 0 over 30 minus 0, and again, using the values from the chart, 16 minus 10 over 30, or 6/30, which is the same as 1/5. Since the average rate of change equals 1/5, and there exists a time t in this interval from 0 to 30, such that A prime of t, the instantaneous rate of change, must also equal 1/5. All right, we're in part C. Part C gives us a function g, which represents the number of gallons of olive oil in the tank. And we are asked to find the absolute maximum on the time interval from 0 to 35. So we are asked to find the time t when the number of gallons of olive oil is an absolute max. So we've got to take the first derivative of our given function g, which is going to be 5 minus 2/3, and we're going to apply power rule, which is 3/2 t plus 9 to the 1/2. We're going to clean that up algebraically, and we're going to set it equal to 0 to find the critical number. So 5 equals t plus 9 to the 1/2. We are going to square both sides, and we find that 25 equals t plus 9. Solving for t, we get t is equal to 16. Now, our candidates for the absolute extrema are going to be our critical number, t is equal to 16, as well as our endpoints, t is 0 and t is 35. And we're just going to find g of 0, we're going to find g of 16, and we're going to find g of 35. I'm just going to do that in my calculator. And we get those values 10, 24 and 2/3, and 8.424. So our absolute maximum number of gallons in our tank is 24 and 2/3, and that occurs when t is equal to 16. All right, lastly in part D, we are to use the local linearization approximation, or the tangent line, using the g of t that's given in part C. And remember, when you're using that tangent line, it's going to use y minus y1 equals m times x minus x1. So we're finding that local linear approximation. And again, that's y minus y1 equals m times x minus x1. Another way to write this in terms of g is g of t minus g of 7 equals my g prime at 7 and t minus 7. So we're finding this local linearization when t is 7. So I've done all my calculations on the right. G of 7 is 20 and 1/3. G prime of 7 is 1. I'm going to clean this up just a little bit to set an equation for g of t. And I get t minus 7 plus 20 and 1/3. Now we are looking to approximate g of 8. I'm going to put 8 in for t. Algebraically, that's pretty easy. G of 8 is approximately 21 and 1/3. Now we're also to find if this is an over and underestimate. So we're looking for a concavity. On the far right, I've taken the second derivative. The second derivative of g of t is equal to -1 over 2 times the quantity t plus square root of t plus 9, which is always less than 0, which is going to tell us we're always concave down, which is going to tell us that our approximation, g of 8, using our tangent line, because this curve is concave down, our estimate, g of 8, is an over estimate. And then here's just a little picture. I'll draw a little picture of something that's concave down, tangent line. If we have a point of tangency and then use the tangent line, it's an over estimate.